morning or evening, afternoon, wherever you happen to be. The Geovariances webinar on uniform conditioning will be starting in a minute or two. As we await for people to join the webinar, you should see a questions option where you're able to type questions. If someone could test that and just confirm that you can hear me. Can hear fine, thank you very much. Okay, let's get underway. The title of today's webinar, Why You Should Use Uniform Conditioning to Increase Confidence in Recoverable Resources. My name is David Barry. I'm a Senior Consultant in the Perth office of Geovariances. This webinar should take about 30 minutes with some time for Q&A afterwards. Questions you can ask using the dedicated questions panel in the GoToWebinar option. And you'll get a recording probably in about 24 hours. A video link will be emailed to you. All of the slides and the demo for this webinar have been made with Izardis Neo Mining Izardis Mining Edition. Geovariance's sort of flagship geostatistics software, replacing the old Izardis that we have sold for quite some number of decades. Okay, recoverable resources. So the context here is that you'll be applying a cutoff grade on selective mining units, so they're quite small blocks. And you want to know the tonnage, metal quantity, and mean grade above that cutoff on the blocks that are above the cutoff. So earlier on in the mining process, you might have some resource drilling, some fairly wide-spaced drill holes. I'm slightly concerned at the screen sharing here. It's taking a little bit of time to for you to see the slides changing as I press them, so I'm sorry if my words are a little bit out of sync with the pictures. But this is the context. So we have some resource drilling, or we imagine that, and possibly what could happen if you knew exactly what the grade was at every block. You could have a reality that looks something like this, and there are some high-grade blocks, there are some low-grade blocks, but you don't have that level of information. We don't know perfectly what all the block grades are. Instead, what we have is perhaps a Kriging estimate on much larger panels. Now, one property of Kriging estimates, they're designed to minimize the variance of the error, is that they usually smooth the grades quite heavily towards the mean, especially when the grades are jumping about quite randomly over very short distance scales. You say, well, the methodology effectively says we don't have much confidence about whether the grade is high or low here, so we're going to estimate something safe somewhere towards the mean of the samples in the neighborhood. And as a result, the possible reality, if you apply the grade cutoff, shows plenty of blocks above that cutoff, quite a lot of tons. But by contrast, the Kriged estimate, there's not so many blocks that are above the cutoff. And that's a general property of Kriged estimates. They're smoother than reality. And so therefore, while the Kriged estimate might be the best linear unbiased estimator, assuming the variogram model is correct, it's typically too smooth to reliably calculate tonnage above a cutoff. And also, you should be Kriging onto panels that are much larger than the selective mining units on which you'll be making your cutoff decisions. Now, for tons above cutoff, what you really need, rather than a best linear unbiased estimate of the grade itself, is an estimate of the distribution of the SMU grades. So that's like a histogram. And then for some cutoff grade, you can say, okay, how much of the histogram is above that cutoff? And that would be okay, I had a comment that the sound had been lost, but apparently it's back. So yeah, you need a distribution, so like a histogram of the block grades, and then how much of the histogram is above your cutoff? Well, that's your tons. Okay, you have to multiply it by the volume and the density to get real tons, but that's how it would go. Basically, once you have a histogram, you have all sorts of quantities that you can calculate from that. The amount of metal above the cutoff, the mean grade above the cutoff. The histogram gives you everything. Now, the problem is, at the start of your project, you don't have the distribution of block grades. What you have is a histogram of point grades, the sample data, and in addition to that, you can get a variogram model. And I'm trying to coax the screen share into updating the slides. Now, that's enough to get us going, because modeling a histogram is equivalent to transforming to normal scores, so a Gaussian anamorphosis. So you match up the quantiles of your raw sample distribution to quantiles of a standard Gaussian, and that's equivalent to completely knowing the histogram. And the nice thing about Gaussian values is that a lot of maths can be done with it. I certainly won't be going into the maths today. It's going to be a short webinar. But a lot of theory can be developed, assuming that grades are Gaussian. So, okay, if you know how to convert back and forth between raw grades and Gaussian grades, a lot of calculations can be done on the Gaussian grades, and that's how the methodology will work. The variogram describes a variability between points, and so if you want to average grades over a block, over an SMU, we have a tool to say, okay, how much is the variance going to be reduced when you average over that block? And with some more maths behind the scenes, this leads to a change of support coefficient. So it's the, in Gaussian space, it's the correlation between an SMU grade and a point grade inside that SMU. And so knowing the correlation between the points and the blocks, that leads with more maths to the anamorphosis model for the SMU grades, and the anamorphosis, knowing the anamorphosis is equivalent to knowing the histogram model. So that also gives us the histogram model for the SMU grades. And so this is promising, because once we have the distribution of the block grades, you can then apply a cutoff to it and then start measuring the tonnages. But at this stage, this is purely a sort of a global histogram. So we're not saying where the tons are above some cutoff within your ore body. It's just an overall, across the whole domain, counting the proportion that's above some cutoff according to this model distribution. So the goal of uniform conditioning is to carry on this idea with a further step. So it's to Krige onto the panel. So we generate a Krige estimate on each of the panels, which are going to be larger than the SMUs. Typically, the panels would be of a size about the sample spacing, or maybe a little bit less. And with more changes support calculations and Gaussian anamorphosis modeling behind the scenes, using the distribution of the global distribution of block grades from the earlier change support, the idea of uniform conditioning is that the distribution, that distribution of SMU grades on each panel is then conditioned on the Krige estimate. So the mean of those SMU grades should be equal to the Krige estimate. There's a bit more going on there. It's you have to work out what the variance is, and the variance will be based on the variance of the estimator, and that can be tricky and perhaps lead to some strange behavior at times, but I'll get into that a little bit more in the demo of things to look out for. The basic idea is that with multiple levels of changes of support, we can go from your original point data and the variogram model to a Krige estimate to a distribution of SMU grades inside each panel that matches the Krige estimate and the variance of that estimate. So schematically, what's going on here is we have panel estimates, and each one of those panel estimates gets turned into a distribution of SMU grades so that it's all in a self-consistent way. Now, the output from the UC calculation itself in Izatis or Izatis Neo is tonnage, metal, and grade above chosen cutoff. So you choose what the cutoffs are on each panel, and at the panel scale, that's what it is. It's tonnages. I've been talking about distributions of SMU grades, but the actual output is going to sort of directly, if you like, to the tonnage, metal, and grade. But if you do want an actual estimate on your SMU block model, so a localized estimate, actually picking numbers from that distribution, that's also possible. You sort of assign a grade to each SMU inside the panel so that you get, I say almost the same grade tonnage curve. It won't be exactly the same because there's only a finite number of SMUs in the panel, so it might not get the grade tonnage curve exactly right. It'll be discretized, but it'll be approximately correct. It'll be a much better representation of the true variability than a Krige estimate, which would be very smooth. And that leads us onto a time for a demo. And so here we have one of the data sets that comes with Izatis Neo, the Carajás data set from Vale in Brazil. It's a iron ore deposit. And so let's think about what the procedure is here for calculating a uniform conditioning estimate. We go to exploratory data analysis. Let me just close these and pretend that we haven't seen this before. So you choose your domain, input data and domain here over on the left. And what we need for uniform conditioning is a Gaussian transform and a variogram. Automatic apply the Gaussian anamorphosis modeling. Won't spend too much time there. Now, if this was a real project, I'd be spending a lot of time at this step, making sure that my variogram was well modeled, because as with everything in geostatistics, it all relies on the variogram model being truly reflective of the data, of what's in the ground. So I'd spend a lot of time here and study the anisotropy and your strike direction, dip direction, etc. But let's imagine that we're satisfied with the variogram model. We've got a Gaussian transform. Those are the two key inputs for the change of support correction. Those of you who have Isatis Neo looking to, or maybe you want to see a demo of this afterwards, technical point, you will need to save the Gaussian variogram as well. We won't be using it for the rest of the calculation. It's just that if you make a Gaussian variable, it only gets saved if you make the Gaussian variogram. Yes, I'll just overwrite what I was doing in preparation. So you have a variogram model. Now I've got two grids that I've already set up, and I'll delete the previous LUC estimate, pretend that I'm doing this for the first time. So I've got a panel grid here of 75 by 75 by 15 meters and an SMU grid of 15 by 15 by 15. So this is 25 SMUs per panel. And what we need first is a change of support. So let's pretend you choose the geostatistical set, which stores the variograms and anamorphosis model that we just modeled in EDA. Block support. This is the SMU block size. This is the size of the blocks that the cutoffs will be applied on. So that's size from file. If that wasn't there, I could sort of drag it in there and it will read the dimensions of the blocks here. Discretization is how accurate you want this, the variogram calculations to be. Standard method, there are two options in this window. The Gaussian one would be used for direct block simulation, so a different sort of change of support. I'm simplifying the overall workflow here and all the different options. So there's an information effect which tries to take into account the fact that you won't be perfectly selecting blocks above or below cutoff. You'll only be estimating them from your final pre-production drilling. I'll leave that for now. That's something you can investigate. Normalized variogram SIL, because there's a variogram model and an anamorphosis model, which is like a histogram model. Both of those define a variance, the SIL of the variogram model and the variance of the histogram. And so you probably want your variogram and your histogram to be compatible. It might not lead to errors in the single variable case. It can certainly lead to problems in the multivariate case if you try to generalize this. So I'll normalize the variogram SIL to match the true variance. If I click apply, I get some graphics. This is in green here is the point anamorphosis model, and in black is the SMU anamorphosis model. And this R value here, this is the change of support coefficient, so the correlation between point and block grades. R of almost 0.95. This is a very gentle, low nugget variogram model, so the correlation is very high. If you were to do this procedure on gold grade, it's very nuggety. You would have a much lower change of support there. Very different distribution of block grades compared to the point grades. You can barely see in the modeled histograms. The gray here is SMU. It's just a hint that there's more of this distribution a little bit away from the upper edge and a little bit down towards the mean. Press run and it prints a little grade tonnage curve to the application messages. And most importantly, it updates the geostatistical set. So now it has a block anamorphosis. So this models distribution of the block grades. I go to the interpolation menu and uniform conditioning. And let's close that. Choose the geostatistical set. The software knows what data I used to model this, so it automatically pre-fills the input data. The output data I would have to choose manually. And we have a localized uniform conditioning option in the same window. Choose the SMU data table. This block size has to be the same block size as was used in the changes support calculation for the geostatistical set. Otherwise, the calculation would be inconsistent and the software will not let you proceed. So it does little validation checks as you go to stop you doing the wrong thing. Now, again, at this stage in a real project, the neighborhood definition, I would spend some time trying to make sure I've got a good Kriging neighborhood doing K&A. But this is a short demo, so I'll hope that this is a good neighborhood. For Rosada's Neo purposes, if you were doing the full K&A here, you'd be in the Kriging window, and that's where all of your main K&A outputs are, your slope of regression and weight of the mean and negative weights and so forth. Uniform conditioning parameters, block discretization, how much you want to discretize the smaller blocks. You choose your cutoffs. So I haven't shown you a histogram of these grades. If I go back to EDA, it's very high grade. So the mean is about 65% iron in this domain. So we're putting some pretty high cutoffs here. We put cutoff 0, and let's say we do 62 and 65. Now, if I press OK here, it's letting me continue. Okay, and I don't use the smart cutoffs for LUC. It tells me there's an error. I can't calculate LUC reliably with this set of cutoffs because the LUC estimate is going to be based on the distribution defined by these cutoffs. But the distribution doesn't stop at 65%. It goes higher than that. So for the LUC estimate, I would need to add something higher. Then it's happy. Then it says there's a whole distribution. Now, this is not actually going to be a good set of cutoffs for the UC. For the LUC. It may be the case that these 62% and 65%, they're the important ones that I need to model. So they could be fine for the uniform conditioning itself. But for the localized estimate, we'll see that this should give us some pretty unsatisfactory results. The other option on this page is the number of ISO frequency classes. This one is defaulting to 1. You can put 5, 10. I don't know if there's a standard rule of thumb. I think 5 is my usual case. What this is about, in the change of support using the panel estimates, the variance of the estimator is going to be used by the algorithm in the background to tune the change of support. So there will be a different correlation between your block grades and your panel estimate depending on how good the estimate is. So if it's a very good quality Kriged estimate, then it should be a very high correlation between the block grades and the panel estimate. But if it's a poor quality estimate, it'll say, well, I don't really know if the SMU grades are close to this estimate. They could be quite wide. You don't know. They could be much lower. They could be much higher. So if you would increase that to 5, that would do 5 different changes of support for the panel estimates and try to tune the UC results to the quality of the different panel estimates. You have to be a little bit careful about results on poorly estimated panels because what can happen is, okay, you estimate a panel, it doesn't have many samples nearby, it gets a low grade. The UC says, well, okay, it's a low grade panel estimate, but I'm also not really sure how good that estimate is. So actually the SMU grades could be a lot higher than that. And so it starts giving you some tons above cutoffs, even though above high cutoffs, even though the panel has a low grade estimate and it isn't well estimated. So you have to be a little bit careful about that. You don't really want to trust the results too much in cases where the panel was poorly estimated by the Kriging. Output, save Kriging outputs if you want, neighborhood name, and let's display the results. And because it's a small data set, this calculation doesn't take too long. And we get some results. I'll turn off the LUC estimate. Let's look at the tons. Okay, at 0 cutoff, the ton is 100% everywhere. At 65% cutoff, we start to see some variability through the ore body. And this would be sort of that's the output of the UC. I said earlier that while this cutoff is perfectly fine, this is the output from the UC. It's your tons, you've got your metal, you've got your mean grade. I said those cutoffs would be bad for the localized estimate. If I make a histogram of the LUC estimate, oops, let's turn that label off. You see you got a spike here, 2 spikes in the distribution. This is entirely because we didn't have enough cutoffs in the for the UC. So there's not much definition on the distribution of the SMU grades inside each panel. As a result, when it tries to generate this LUC estimate, it doesn't have many fine-grained values to choose from. So 2 ways to fix that. One is I could go in here and I could type lots and lots of grades in there, or I can check this button, use smart cutoffs for LUC, and it'll add a lot of different cutoffs and probably take a little bit longer to calculate. Not too long. And what we should see with the much finer definition on the distribution is a much better histogram on the LUC results. There may be some issue here, one little spike, but this is obviously much more realistic than what we had previously. And that's the quick tour of uniform conditioning in Exartis Neo and localized uniform conditioning. If I go back to the PowerPoint and hope that the screen share carries on to my summary slide. So let's see if I can coax it into moving. So the summary points, so uniform conditioning, I jumped too far. I apologize for the slides jumping around. Uniform conditioning offers a geostatistically sound way to estimate recoverable resources. It's based on the variogram model. And it's much faster computation time than conditional simulations. So recommendations: have a reliable variogram model and Kriging neighborhood. Beware of tonnage from poorly estimated panels. If you're doing a localized estimate, make sure you have plenty of cutoffs for it. As a general rule of thumb, at least as many cutoffs as you have SMUs per panel. And something I didn't talk about, but don't trust the exact location of the LUC estimated grades within each panel. They get assigned according to the rank of a Kriged estimate. but it's not necessarily the case that that's realistic. It can very much lead to artifacts. It's really just about having a block model with the right grade tonnage curve. So I think some of you have already been typing questions as I go. We'll have some time for Q&A now, and so while you're thinking about your questions and typing them in, I'll just say a few words about geovariances. Software vendor, industry leader in applied and advanced geostatistics. We have an exclusive technical partnership with the Center for Geostats at MinPayTech, the Paris School of Mines, founded in 1986. So if you round up to the nearest 5 years, that's 35 years experience in geostats and software development. Got 40 employees, technical experts, consultants, and software developers. We've got offices across the world now. The main one for us is in Fontainebleau in France. I'm in Perth. Belo Horizonte in Brazil has a few people as well. And our consultants can help you implement these methods and various other aspects of the mining or geostats part of the modeling process: resource estimation, resource classification, uncertainty characterization, and drill hole spacing optimization. And we have some upcoming training courses if you want to get into much more detail on this subject material. Recoverable resource estimation, online course in the European time zones, September 3-4, in Perth in October 8-9, and more later on. Geostatistics Neo fundamentals course to learn how to use the software. We have plenty of dates for that. More info at our website, geovariances.com. Various users of our software. And if you want to have your own demo, you can contact Marlene Wologroski, Marie-Cécile Fedve, Gustavo Acero, depending on which part of the world you're in. And after the webinar is over, you'll be prompted to fill in a feedback form, which we'll be very happy to hear from you, your feedback on the webinar, what you'd like to see, what could be improved. And now I get to have a look at your questions, and there are quite a few of them. Nicolas asks, can this be applied if we calculate densities? And wow, I've got to think on my feet here. I feel like the simplest way to apply this would be to estimate the density separately, or maybe co-Kriging density with grade. There may be issues there. The simplest way to do it, you would estimate the density into your block model, and then the tons that are output by our software will be on a 0 to 100% scale, but you could use your estimated density and the volume of your block to turn that into real tons. Exactly how you take into account the density in the estimate of the grade as well, that's not immediately obvious to me. You can extend the UC to multivariate, or whether it's correct to, or how it's best to do that, I'm not sure. I would have to give that more thought. Anil Kumar asks, is the Gaussian anamorphosis done on histogram of block grades, and how is it back transformed to the original histogram? At the EDA step, you do the Gaussian anamorphosis on your point grades, and then the change of support tool, the support correction, calculates using the variogram model what the anamorphosis would be on block grades, even though you don't have direct access to what the block grades are at that stage. You don't have an estimate of them. You just have a distribution of point grades, but it works out what the distribution of block grades would be based on your point distribution and your point variogram model. And it makes some assumptions about bivariate Gaussian so forth after computation. So that's how it works. It's a theoretical calculation. And Anil also asks, in the case of a gold deposit where you've got 50% nugget, how is the uniform condition carried out? The methodology is the same, the steps are the same. Obviously, it would be a lot more difficult to compute the variogram and model the variogram. But what ends up happening is you have a much smaller change of support coefficient, so you have much worse correlation between your point and block grades because the block grade is averaging so much more random behavior. And so you get very different looking block distributions to your point distributions. But in principle, the calculation carries on in the same way. Vic says, might be useful to discuss some of the required properties of the mineralization and variables, for example, by Gaussianity and diffusivity to test for applicability of LUC for mode of mineralization. So yeah, this gets into the sort of the theoretical underpinning of the method. So in contrast to MIK, for instance, multiple indicator Kriging, which assumes sort of a mosaic model where grades can sort of jump quite rapidly between different grade classes. UC is assuming that you have diffusive grade distribution. So between a low grade region and a high grade region, the grades will sort of gradually move in between them. Obviously, there can be point-to-point variation with the nugget. But yes, that's a correct comment on the theory behind the scenes. Anil asks, is the range of the variogram in the vertical direction taken into account while choosing the size of the SMU? It says in gold deposits, the variogram range can be very low vertically. I would say, for me, certainly the way I approach this is that the SMU size is kind of determined by your the requirements of the mine. It's not really a free parameter for what I have to do. I'm told that, oh, you know, this mine site will be mining on blocks that are of this size. It's nice certainly to have the compositing length of your data compatible with the height of the blocks. But once you have those two, the rest, I wouldn't personally need, I wouldn't worry about tuning the block size of the SMUs to your range of the variogram. Yeah, so panels you can sometimes want to tune the size of depending on the range of the variogram. Like if you have a very low nugget long range variogram, you can get away with smaller panels. But the SMUs within the panel, really you're just asking, okay, what's the distribution of those grades? So I think for that case, it's not something I would worry about. Another question, how to deal with multimodal histogram. The Gaussian anamorphosis should handle that. I mean, probably really you'd want to domain it properly. If you've got two modes in a histogram, it's probably a domaining issue, and a lot of geostats assumes that you're in a stationary domain, and you might not be in the case of the multimodal histogram. So I would say maybe go a little bit upstream to make sure you're working in a nice domain. But in principle, the anamorphosis can handle that. It can model the shape of your histogram as it is. Rodney says, challenges with multivariate assessment, practical limits on the number of ore and contaminant analytes. Yeah, the other thing, while the UC can be extended to multivariate, it's not true multivariate. It's a series of bivariate estimates with the primary variable. So that's also another limitation on the extension. David asks, if you use LUC within a nuggety gold deposit, how does it handle the outlier value? Yeah, this is a problem. UC assumes that you have a reliable variogram model, but it's how do you get a reliable variogram model when you have severe outliers? Are top cuts required? I mean, in practice, I would top cut. That does mean you're going to lose some of the metal in your estimate, but it's yeah, the alternative would be, and it's not strictly speaking correct, but the alternative would be modeling or doing the variogram in Gaussian space and back transforming to raw. But that probably has its own issues with the anamorphosis modeling of the tail. So yeah, it's an issue. Sout asks question about variogram calculation, why we need to calculate the variography in Gaussian space. That's purely an Isatis Neo software issue. The theoretical calculation uses the raw variogram and the Gaussian anamorphosis. And it just happens to be the case that the way our software is designed is that if you want the Gaussian anamorphosis to be saved in the same geoset, you need to switch on the Gaussian variogram. So the UC calculations themselves are all done, or the change support calculation is done with a raw variogram. Fisco has a long question. Let's see, what's this? What's the difference of the product if we use UC, LUC, and ConSim? So UC and LUC should give you pretty much the same grade tonnage curves. The LUC is designed to give you the same. Conditional simulations, you would hope that it gives you reasonably close results, but I mean, you would be, with conditional simulations, you would be modeling in Gaussian space, simulating in Gaussian space, and back transforming at the end. So you're sort of directly getting the full distribution of block grades. So it would be a much larger computation. You could do a lot more with it, and you would hope that the results are reasonably compatible. But because you're going a different path with the Gaussian variogram model and the back transform, it is possible that that you get some differences. Is there a problem with using UC to estimate in a high nugget effect? Yeah, it's come up a few times. In principle, that the methodology can handle it. Whether the results are good or not, it's difficult to estimate these things when it's really high nugget, and there may be questions about how, actually accurate it is. And a cluster drill hole distribution, you would probably want declustering weights at least on the anamorphosis. But in principle, it's not an issue. And then there's a question of how to validate the estimation from UC and LUC. You can, okay, you can do swath plots. You can check against the Kriging estimate. You check that the means are appropriate, that the trends are appropriate. But I mean, ultimately, you're not going to be able to validate it ahead of time. You have to hope that your modeling was correct. But it's yeah, it's knowing, can you fully validate it ahead of time? To me, that's an unknowable. Is it recommendable to use it for blast holes in a short-term planning model? It's not something that I've done, and I think for short term, you've probably got enough definition on your, the blast holes are likely close enough that you're getting pretty close to the true distribution, even from Kriging. So I'm not going to say absolutely not, but it seems like that's not the use case for it to me. Fernando asks, how about dilution when you use big panels? Yeah, if you may need to multiply your tons by a proportion. if you can calculate your dilution proportion somehow. And beyond that, I don't really have any comments. Andrew asked, when should you not apply UC? Wow. I mean, it may be the case that a method like you find that MIK is more reliable in the variogram modeling to get the full range of the metal with something with a very skewed distribution. That's possible. If you want, and I guess the other thing that Vic mentioned earlier with the it assumes a diffusive model. So if you've got mixed populations, that might be sort of breaking some of the theoretical assumptions for the UC and its variogram modeling, etc. That's probably what I would say there. Fernando asks, the UC is only for a big disseminated deposit. I don't. I guess I have done it on narrow vein gold. I'm not sure how fully applicable it is in all cases. To me, the mathematics of it is reasonably sound. So I don't think it's necessarily the case. It may be the case that for practical usage, it's better in the larger deposits, but I don't think there's any theoretical reason that you can't. Other people may disagree. And we had a lot of questions today, but we've got one more from Andrew. Is there some kind of test for saying a distribution is mosaic rather than diffusive? I believe the standard test for this is something like the calculating the cross variogram divided by simple variogram ratio for a series of indicators. And if you've got a mosaic model, I believe that ratio should be flat. And then that's probably a more technical answer than a lot of people were hoping for. But that's the best I can do off the top of my head. And yeah, okay, we will get a copy of all the of the questions, and so I can send that by email. So thanks to all of you. That was a well-attended webinar, and you had a lot of questions. So thanks for all of that. You'll get a feedback form shortly. And now all I have to do is work out how to end the broadcast. And thanks for turning up to the webinar.